and then we'll talk about chapter 12. And so chapter 12 and then the rest of the content is a cumulative thing will be on the
Yeah. But I mean, we're almost caught up. Like,
we're almost caught up for sure. Yeah, we might have to spend a little bit of time on Tuesday talking about 11.4, but 11.4 is fairly short. So do y'all have any homework questions? All right, we were in just started 11.2, and here in 11.2 we're looking at a given series. At this point, not knowing what function it represents, we sort of start looking at that in 11.3, wanting to know whether the given function or the given series converges, and for what values does it converge. So remember, the interval of convergence is that series domain. Right? So when we say this series equals this particular function for this interval of convergence, that's the domain where the series and the function are the same. And we applied the root test. Did anyone have any questions on what we've done so far? Apply the root test, and we said, well, here's the root. It has to be less than 1 for convergence. So we're just solving that inequality for x and getting the fact that x has to be between 3 and negative 1 and 3, rather. Anyone have any questions about that? All right. So I'm going to back up to our two tests. It's not geometric. We're using the ratio or the root test. And we said that either one of those tests, the ratio or the root test, is inconclusive when the root or the ratio is identical to 1. So what that means for us is that when we apply the root or the ratio test to a series and we say, this is the interval of convergence, it's always part of the story. You always have to test these endpoints to see if it converges or not. Let me see if I have a link over here, so I'll just illustrate this. So we said that our ratio was equivalent to the absolute value of x minus 1 times a half. And let's just say for a moment that it was identical to 1, not less than 1. Sorry, we have our half here. So what that means is, we should note as well, the test is inconclusive. So meaning the test doesn't give us any information. It's inconclusive. Yeah, we're starting with our ratio. And we said for convergence, it has to be smaller than 1. But I'm just going to try to show you, like, if the ratio is identical to 1, what x values we end up with. So that's the same thing as the absolute value of x minus 1 equals to 2. Which means that x can be 3 or what? Negative 3 minus 1 is negative 4. Absolute value is 4.
Oh,
Negative 1. Mm-hmm. So that our ratio test or root test, whichever one, either one, when x is 3 and x is negative 1, it doesn't tell us anything, meaning it could converge or diverge when x are those two values. So notice those are the two values we got here on our endpoints, which is why we made the note on the previous page. When you use the root or the ratio test, you always have to check your endpoints for convergence or divergence. We're going to check the endpoints. And what that means is we're going to take x equal to negative 1 and x equal to 3. plug those into the original series. And then look at what series results, whether the series that results from x equal -1 and x equal 3 is a convergent or a divergent series. So plug those into the original series and determine if the corresponding series converges or diverges. So that's what we mean when we say test the endpoints. All right, so doesn't matter where we start. Let's take x equal to -1. So our original series was the sum from k equals 0 to infinity, -1 to the k, times x minus 1 to the k over 2 to the k. Okay, so we plug -1 in for x and determine that particular series, does it converge or does it diverge? What do you think? Okay, so it's helpful to then simplify this. Does everybody see that's going to be equal to 1? So the -2 to the k, I'll just write it out again. The -2 to the k, we're going to rewrite as -1 to the k times +2 to the k over 2 to the k. So the 2 to the k's divide out. We've got -1 to the k times -1 to the k. We just move the -1 times -1 to the kth power, and you get 1 to the k, which is 1. Okay, so that's equivalent when x is -1, it's equivalent to the series from 0 to infinity of 1. Does that converge or diverge? Do what? So remember what that means. What does that mean? There is no k, so what happens in that series? It's just 1 plus 1 plus 1 plus 1. Right, so this diverges.
So why'd you split it up?
Just so we had a better sense of what it actually was.
Couldn't you just cancel out that 2 to the k? That negative 1 stay there.
Yeah, you can cancel that out. -1 stays there. -1 is the same thing as -1 to the k. If you see that, that's fine. So since when x is -1, we get a divergent series. What that means is we're going to keep excluding -1.
So the endpoints should diverge, or the middle be true, right?
Depends on the series. So we'll just say exclude x equal to -1 from the integral of convergence. Does anyone have any questions? Do the same thing when x is equal to 3. So when x is 3, does that given series converge or diverge? So -1 to the k, do y'all agree? Diverges? Okay, so that sum, depending on how many terms you add, if you add the first 2, you get 0. You add the first 3, you get 1. 4, and the next 4, you add -1 to that, so it's 0 again. The sum is either always 1 or it's 0. So it doesn't have a finite value. It's basically, you can view it as the sum, depending on where you stop, is 1 or 0. So this diverges as well. No, the series converges. We came up with the interval of convergence from -1 to 3, and we were just testing the endpoints to see, does that actually indicate that we could include either one of those endpoints as part of the domain. So this interval of convergence is still valid, right? Because that's the interval for which the ratio is less than 1. So we still have convergence on that interval. But what we've done here with testing both of our endpoints, and both endpoints resulting in a divergent series, notice it's a divergent series, it's not a divergent power series that involves the variable x, right? These are just straight series. They don't have any variables in them. So all these mean is we're going to exclude these values from our endpoints. We're excluding 3 from the interval of convergence.
Series convergence, like -1 and 3, like.
Right. Not including the endpoints. So the interval of convergence. Do what? Yeah, so we actually have found the radius in this step right here. We have the absolute value of x minus our center is less than 2. So our center is at 1, the radius is 2. The radius of convergence is 2.
What's the center?
No, because it's x minus 1. So it shifts it over to the right 1 unit. So if we would just say r is equal to 2. So we're looking at this interval, -1 to 3. And if we're 1 unit at the center, then over this many is 2, and over this many is 2.
Possible to see that on a Wolfram too.
like that function just what that looks like as a function? Let's think about that. See, as we start adding more and more, let's look at it this way here. As we look at it just a few terms, it might be a little bit difficult to tell where this converges. And perhaps we can plot this from -1. But let's go from -2 to 4, yeah, or something like that, just to see if that kind of helps our vision. But when we start adding more and more terms, we see that function, or that series rather, is kind of squeezing into its domain, right? So here, we've kind of, it's kind of like this vertical asymptote. See how that just keeps moving up and down, moving up and down. Let's look at it from actual domain. Let's go maybe, I mean, it's really not going to show us much more if we keep going out further. So there's 50. So it doesn't, it's like after that value, there's nothing happening. I mean, granted, that's the window we plotted it on. Even if we get rid of that, right? So we see all of this stuff, you know, kind of working its way up to, I don't know, it's one of the software. But there you go. There's that function as a series plotted for the first 100 terms. It's just now catching on. But you see that it's squished in that window from -1. So that's the domain of that function, just like the domain of any algebraic function. You don't see the function outside of its domain, right? So that's what we're dealing with when we find these kinds of things. And it's important because if we say this series represents a particular function, we're saying that this series represents that function only when we're inputting values that are in this interval here. If we plug in a value like -2, the function is still the function, right? But the series does not match the function anymore. So we can't say that they're the same thing outside of that. Yeah. Are there any other questions on that example? Okay. So this theorem tells us basically the power series converge in one of 3 ways. Converges absolutely for all x, like we saw with that first interval x, or series rather, x to the k over k factorial. That converged for all values. It can converge on an interval as specified in item 2, which was our last example, converged in a particular interval. Or it can converge only at a point in which, at A, its center, in which case the radius of convergence is 0. So those are the 3 ways a series can converge. we've seen an example of the first two. Let's look at example 3. Let's find the interval and radius of convergence for k factorial x to the k. So the test for convergence we use here is what? The ratio, because the factorial. So we're going to compute the ratio. K approaches infinity. Take the absolute value of the k plus 1 term. Multiplied by the reciprocal of the kth term. Oh, yeah. Yeah. So this is, yeah, well.
But we've done an example so many times.
That was all jacked up. Okay, that's better. So since k is going to infinity, anything that involves k you can pull out of the absolute value. It's really the things with x that we need to keep in the absolute value. So this simplifies to what? Yeah. Absolute value of x times k plus 1. Y'all agree?
So let's keep that.
Yeah,
Why is
absolutely.
k plus 1 not a?
Because k is out here at infinity, and we think about k starts at 0, 1, 2, 3, 4, 5. Yeah.
You wouldn't really need the absolute
But what does this limit give us? Infinity. So what does that mean? Well, so if x is like some number, and we can refine this, but if x is some number, isn't the ratio always larger than 1? So for any value of x, wouldn't that always diverge? Does that make sense? You have to be a little bit more careful than that, though. Can anybody see it? The only value of x that would cause this series to converge would be what? 0. Right? Because we're thinking about k plus 1 is, it's k, it's 1, it's 2, it's 3, it's 4, it's getting larger and larger, right? But if x is always 0, then this is 0 times a billion times a trillion. It's always 0. So we don't want to look at it in the context of like a normal limit that we've seen outside of this region here. It's always been an indeterminate thing. Infinity times 0 could take on any value. But in this context, where this k is just this index coming from the series, and that's always going to be 0 when x is 0. If you want to think about this in two cases, you've got the case where x is equal to 0, and the second case when x is not 0.
We really have to solve for x.
Yeah, well, I mean, there's really nothing to solve for once we've noticed that, because in case 2, when x is not 0, then the ratio is infinite, which diverges. When x is equal to 0, our ratio will be 0, which of course is less than 1, which converges. So we only get one value of x that makes this series converge. We don't get all real numbers like we did in that first example. nor do we get an infinite set of x values within an interval like we did in the last example. It's just one x value.
How does it really convert then? I mean, that x equals 0, it's not zero.
Well, so yeah, if k running from 0 to infinity, we have k factorial times x to the k. That's the series we're looking at if x is 0. And that's always 0. It's 0 plus 0 plus 0. That's a convergent series. It converges to 0. Does that make sense? I'll take that as a yes. Okay. Does anyone have any other questions on that? Yeah.
So would the interval and radius of convergence be equivalent? That's just 0.
Yeah. So we just have, so and then what we're looking at is we've covered all three of these. This item 3 in that theorem, the series only converges at a, or x equals to 0, in which case the radius of convergence is 0, and the interval of convergence is 0. There is no interval. So it's just like, I guess it's a matter of notation, but it's set 0, I guess, and then the radius is 0. I mean, interval of convergence and radius of convergence. And naturally, those series, like the series that converge at a single point, are totally useless to us if we're trying to approximate a function. We want a series that's either item 1 or 2 in that theorem, converges for all x, or some x within a particular interval. It doesn't do us any good to have a series that represents a point. Other questions about that? All right, y'all try this one. Yeah.
Entity is, it's gonna be.
The limit applies to
So one order is affected.
the root order ratio.
Take your. Take that. Right, basically that. I think. Yep. Oh, okay, I see.
Which is a very loud, very standard.
Oh, yeah. But where else? Same, because I'm thinking like growth rate. So we think about this. It's probably 10 billion. That's a little. So as you get higher and higher, that's what's different. Argos 1, I was thinking this is a lot of birds. But it depends between these two. So the ratio is this is like the square root of 2 square root. How much? So I think Argos is
That's why I was like. This is the hey, certainly a good one, so then that's a good one. Which is funny. One.
About square root of k plus 1 square root of k over k plus 1.
My brain isn't keeping
Times 2, 0, plus 1 second. Yeah.
no, I know.
What's your, this is
Yeah.
What's your name? This is my go-to. So now you're like, now will be what's happening here. Can you use the top down and then
Yeah, so like, I mean, if you get there on the over.
Now I know.
I just, you know, I'm just like, well,
You're right. But people know on either side. Well, no, that's what the epsilon. This is correct. This is the problem.
yeah, we were like.
But we all know, this is why I told you that we'll get to some values. You know,
No, I know, it's just like.
and you literally, for this one, you literally just treat it. Go to the top. Yeah, I know what you mean.
I thought it was like the over dx.
No, and basically, you're right. That's not how it's the other summation. One over two. Okay, so, yeah. We're not taking.
Yeah.
Are you sure?
is our ratio.
I do know.
I got to hear. That's just weird. I already just won. Does that just mean that it's
All of
Well, actually, I'm saying
That works out. Okay, so, I guess I don't understand what it's telling me now.
Okay, so for
in the way that you
if you're, if your ratio is we're testing the absolute value, so that's the ratio. So that's what we come in and say, we're inserting that, we're testing for conversions. The test will only ever give us because we have to say, I want this to converge, so this has to be less. And now we have this solved, which gives us our interval.
So you just add two to that side.
Yeah.
And then, you have to subtract two.
Right, yeah, so remember like this thing, less than.
Yes.
That means that x minus a is less than the number, but greater than the negatives of that number. That gives us what we solve for x.
Evaluating. Wait, so these are the values that matter when you're evaluating.
Yeah, I was like, what does this tell me? I have data, what does it say?
Don't forget to test your.
Based on that.
You should have asked.
I would have. Yeah, that's right, and he kills him.
Those honestly piss me off.
So like, okay.
So on the left side, you have all three. One, get off the one. But since it goes narrow, would this be really approachable? Yeah, it's saying like why is it basically the limit of negative one yeah, just like once. Oh, right. So they wanted to say negative and altitude just say yeah. So this side is that it's and then
So this, and then, if you get one close, what is that represent the close one?
So, yeah, so what is?
That would also
Wait, this is equivalent to a P series.
So wait,
So it doesn't.
Basically starting.
wait, series.
I would assign you that.
Because
In between the gap. I seriously.
why don't you just
No, P series would be, but well, I mean, K, I'm talking about like a P series. K is 1,000. So.
Oh, yeah, that's.
This is one greater than. I'm sorry, if it's greater than. So this side looks like that. So it does not include. If it's just less than one. Yeah, because like a series of 1 over K diverges.
Oh, right, so yeah. That's where I was like.
Okay, the way I think about it is like, so 1 over K, that's a harmonic series. But like if you set the number bigger, like 1 over K squared.
well, you're saying over.
There's
How, I mean, how's the limit? I'm not talking to you actually.
so mine is converges.
That was my review.
Yeah, whatever you. About that one. So you. Or radius.
This is cool. Oh. That
It was because of business.
That's the reason why. Oh, I see.
Which I'm assuming is going
Yeah, well, yeah, it's hard for me to or what my yeah.
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 All right, if you want to think about this for a little bit longer, think about it for a little bit longer. We're going to take a break, come back and talk about this problem. Yeah. Do what? What do you mean?
It's like I have no clue. So, how to determine is a K plus B plus A?
So you would have
Is a K.
base of k is 1 over root k, and base of k plus 1 is 1 over root k plus 1.
Oh yeah, okay, so that's less than.
Yeah.
Oh, really? I'm sure I'm great.
There's actually a song, like a bunch of kids. Not like any of you. It's like a Mexican kid. It's like when you get like everyone's like
So how do you know which one to use, the ratio or the root?
So I would use the ratio here because although the x minus 2 to the k would be eliminated with the root, the square root of k would not be. So then you have another level of complexity in evaluating down the root. Yeah, right.
You generally only want to use the root test when all of the k's will be canceled, or the exponent of k's will be canceled.
Yeah. So like that, I mentioned to many of you that the one example where we had something to this effect, we did the root test because they were all to the kth power, and the root knocked out all of those k's for us. You know, if this were like even x minus 1 to the 3k, when we take the kth root of that, we're dividing by a k, so you just have x minus 1 cubed once that root is applied. So in that example, that's the reason why we applied the root. Here, if you apply the root test, as I mentioned to some of you as well, there's nothing wrong with the root test. It's just with the root test, you end up with, you end up with the absolute value of x minus 2 times the limit as k approaches infinity of 1 over, you have the kth root of k to the 1/2. So you have k to the power of 1 over 2k, and the denominator here approaches an indeterminate form, which then we have to use L'Hopital's rule. So you have to say, okay, well, that's equivalent to e to the 1 over 2k times the natural log of k. Evaluating that limit as k approaches infinity, we're just looking at the power at this point. We have that limit evaluating to 0 times infinity.
On one side, how did you get E?
Take ln
So that's just the process here when you get one of those indeterminate forms like infinity to the 0, 1 to the 0, or 0 to the 0. You have to rewrite it because those always arise from functions of this form, like 1 to the infinity, 0 to the infinity to the 0, etc. And this is just an algebraic trick relating the inverse e and ln. So remember, if I take e to the ln of anything, I just get what that quantity is there in the brackets because they're inverses of each other. So really we're taking e to the ln of f of x to the g of x here. And by properties of logarithms, we have the logarithm of something raised to a power. The power comes out front to multiply the logarithm. So then we look at that f of x to the g of x as e to the g of x ln f of x. That power will always result in an indeterminate product. And then you've got another L'Hopital's rule process for the indeterminate product. So now it's kind of like a separate problem. We have to rewrite this as e to the ln of k over 2 to the k, or 2 times k rather. As k approaches infinity, this is infinity over infinity. And now we can apply L'Hopital's rule directly to ln k over 2k. So it's e to the 1 over k divided by 2. As k approaches infinity, we can look at this as 1 over 2k, e to the 0 is equal to 1. So this limit is 1 over 1, which is 1. Right? It's the same thing you get if you did the ratio test for that limit. Sure, yeah. Sorry, the notation's a bit crummy, but that's for the root test. We're, however, doing the ratio test. So we simplify the x minus 2 to the k plus 1 as x minus 2 to the k times x minus 2 to the first. And then we can simplify the x minus 2's to the k. We end up with this limit times the absolute value of x minus 2. And so if you want to put the absolute value of x minus 2 in front of the limit, you can, because it's not affected by the limit. Limit operates on only things that involve k. That limit is 1. So it's helpful to label these things correctly and keep in mind what we have here. This absolute value of x minus 2 is that series ratio. So now it's up to us to say, all right, well, I'm testing for convergence. For convergence, the ratio has to be less than 1. So this is where we come in and add that our ratio has to be less than 1. You always have to add that in. The root or the ratio will never give you that less than 1. That's our addition to test the condition of convergence. So then we have x minus 2 is less than 1 or greater than negative 1, removing the absolute value. And then we have x is larger than 1 but less than 3. So initially that is your interval of convergence. We'll just note here. Initial interval is this interval, but we have to test these endpoints. Notice here also the initial, or sorry, the radius that we have, x minus our center is less than 1. This right here immediately tells us that the radius of convergence is 1. If this were the absolute value of x minus 2 is less than 1 over 45, your radius of convergence is 1 over 45. It's not always 1, because in another example, we had that 1/2 that was here as a result of the limit. So we had the absolute value of whatever was less than 2, our radius was 2. So it just really depends on the limit that it evaluates to. So testing, what's the series? Yeah. So when when x is 1, we have 1 minus 2 to the k over root k. So we want to know, does that series converge or does it diverge? This series that we come up with is only related to the original series in the sense that convergence or divergence dictates what we do to the endpoints only. We already have the interior of convergence. So no matter what, we know it converges on that interval. We're just trying to see if we pick up the endpoints through this process of testing the endpoints. So we have that as the sum of negative 1 to the k over root k. And so that's an alternating series. You have to use the alternating series test to justify its convergence or divergence. And remember that a sub k in the definition or the theorem that defines that was the part of the series that did not include the negative 1 to the k plus 1 or whatever. So this a sub k is just 1 over root k. We leave the negative 1 or the switch out of its alternating series test. Yeah.
So it doesn't have to be negative 1, right? It can be some other negative number, maybe 5 or something.
Yeah. So like if this ended up being negative 5 to the k on top, we could view that as negative 1 to the k times 5 to the k. So like if it were this, let's say, then our a sub k is 5 to the k over root k. In which case this thing would diverge, but just to see a different example. So test that. First condition was that the next term had to be less than or equal to the previous. So what we're going to say here is, since the square root of k plus 1 is strictly larger than the square root of k, remember k is 1, 2, 3, 4, 5. Since that's true, 1 over the square root of k plus 1 is strictly less than 1 over root k. So that condition is satisfied. The next term is less than the previous. second condition, again, not to be confused with the divergence test, the second condition in the alternating series is that the limit as k approaches infinity of a sub k has to be 0. Why is that not the same as the divergence test with an alternating series? If it is 0, then it is inconclusive, the divergence test. Any other comments on that? Why is that not the divergence test for any alternating series? Yeah, so if you do end up with a 0 with a divergence test, it's inconclusive, right? Really what I'm after is the divergence test, let me just write it separately. The divergence test for any series, no matter what that a sub k is what we have here. But this a sub k isn't the entire series, is it? Because we left off the alternating part. So the divergence test applied to the alternating series looks like this. Limit as k approaches infinity of -1 to the k over root k. That's the divergence test applied to that series. We're only applying the limit as k approaches infinity to a part of that series.
So for, you pick A of K, is A of K, you always use out that alternative?
Yes, correct. In the alternating series test, right? So hopefully you can just look at that and know that that's going to be 0. See how much stuff we have. Maybe we can go a little bit more without making that illegible. All right. Therefore, when x equals to 1, we get a convergent series and again, that was by the alternating series test. We include x equals to 1 and unabbreviate the interval of convergence. So initially our interval of convergence was from 1 to 3. That particular test tells us now that our interval of convergence is -1 to 3, including 1. And we're going to test 3 to see if we can close that off or we leave it as is. Do y'all have any questions at this point? I'm going to start another page here. Just so that page isn't illegible when if you print it out. Okay, so that gives us the sum 1 to the k over root k. 1 to the k is always 1. So that's a series 1 over k to the 1/2. That's a divergent p series. the P is less than 1. For a P series to converge, the power 1 over, or whatever, some number over k to a power, the power has to be larger than that. That means we exclude x equal to 3 in our interval of convergence. So finally, our conclusion is that the interval of convergence is from 1 to 3, and the radius of convergence is at 1. So yeah.
Do you always have to show the like brackets and parentheses, or do we show as an inequality?
Yeah, I did. So I would think that if someone's being particular, you'd want to show it as an interval because it is an interval of convergence versus the inequality. Which one did I show as a?
When you did, you put it down.
Oh, all right. Yeah, I was gonna have to correct that. Okay. Do y'all have any questions on that?
Why did when x equal 1, like why was that the opposite of what I thought it was?
What did you think it was?
I think I had diverges written down. You said that convergence.
Yeah, so when x equals to 1, we ended up with this alternating series. So we can check those two conditions, which were both true. So it converges by the alternating series test. I can capture all of that in the same screen. So that condition was true and that condition was true. So if either one of those conditions are false, you have a divergent alternating series. Or to converge, both of those conditions have to be true. So any other questions or things I could clarify? You see a lot of this stuff on chapter 10, the series test, coming back, particularly when testing the endpoints for these intervals. The two primary tests we use to get those intervals are the root or the ratio test, or if it's geometric. Primarily root and ratio, they're applicable to a large variety of series. But then like any other series test could show up as a result of testing the endpoints. So that's a summary. I know it's a very general way to state all of it, but we use the root or ratio test to find the interval of convergence. Where do they say? Yeah, so here in this last bullet, they're talking about this is our initial interval of convergence. And it says that possibly both of its endpoints converge on the interval and possibly one or both of its endpoints. So again, that's implicitly what this is saying is it's not guaranteed. That's why you have to test them. So yeah, for whatever that's worth, if it's worth anything to you at all, it's there. So just to point out what the following theorem was going to say. A power series defines a function on its interval of convergence, and we can combine power series. So when they're combined, algebraically, new functions are defined. Just like when we add two functions of x, you get another function of x. You multiply two functions of x, you got a new function of x. The following theorem is stated without proof, gives us ways to combine power series to obtain a new power series or new function by using particular operations with two power series, or more than two. So it says, suppose that the series c sub k here, they're just coefficients, x to the k and d sub k x to the k. Coefficients are d sub k there. Suppose that both of those series converge to f and g, respectively, on some interval. One says the sum and difference, when we add two convergent power series, it's equivalent to adding their coefficients. It does not affect convergence because now the new power series that we've added or subtracted converges to f plus g or f minus g. So if we have one series that converges to like 1 over x and another series that converges to 1 over 1 minus x, when we subtract those two together, the new function will converge to 1 over x minus 1 over 1 minus x. So adding and subtracting is a way we can combine power series to create a new function. Multiplication by a power and composition are the two others that we can combine power series by multiplying by a power of x or composing with something else will give us a convergent series as well. So maybe this is a little dense. Suppose m is an integer such that k plus m is larger than or equal to 0 for all terms of the series. X to the m. So what we're doing is we're taking x to some power and multiplying that by our convergent series, knowing that this series converges to a function f of x. So we're going to take that all of that and multiply it by x to a power. It's usually given, like that'll be x squared or x to the 12th or whatever. As long as the new series power, which is just k to the k plus m, we're just adding the exponents. As long as that new series power is larger than or equal to 0 for every single term, then you have a series that converges to xm times f of x. So remember, this series here, this thing converges to f of x on its interval of convergence. So it's just like multiplying f of x by a power of m. I think maybe it's a little hard to look at something like this and know exactly what it's saying. So we'll look at some examples. And then the composition, h of x is some number times x to the m power, where m is a positive integer and b is any real number as the coefficient. So notice here we're taking this series, and we're saying for x, I'm substituting this function, h of x, b x to the m. So there's my x in the original series. So if I plug in another function of x for that x, the new series converges to the function f of h of x. Okay, so here's an example. I'll reference these with the particular examples. Note that the new power series can be formed by multiplying and dividing. It's just that's a very, very tedious process. Example 77 in the back of this section, 11.2, shows you how to do that. We're not going to deal with that. We're just going to deal with sums and differences, multiplication, and composition. So use the geometric series f of x is 1 over 1 minus x, which is the sum of x to the k. Remember that geometric series is valid, or the domain for that series is when the absolute value of x is less than 1. So we're going to use that series to find a power series representation for the function g of x, which is x squared over 1 minus x, centered at 0. Give the interval of convergence of the new series. Okay. So can you see that g of x is just a power of x times f of x? G of x is just x squared times f of x. Okay, so x squared times 1 over 1 minus x. We know what the series representation for 1 over 1 minus x is. Let me put this in a different color.
So then we need to multiply the.
Yeah. So it's just equivalent to multiplying all terms by x squared. Okay, and we know 1 over 1 minus x was given to us as the sum from 0 to infinity of x to the k. Which is x squared times 1 plus x squared, etc. Just note that this is for the absolute value of x less than 1. Therefore, what we have is x squared over 1 minus x equals to the sum, k equals 0 to infinity, of x to the k times x squared. We just add their exponents, so x to the k plus 2, which is equal to x squared times 1 plus x squared times x. So you've got a completely new power series that converges to a completely different function just by multiplying the original by a power of x. Because we combined, we combined x squared with x to the k. Okay, so that's our new power series. What is the interval of convergence? We're using the second rule. It's multiplication by a power series. The new series that converges, remember this is what we're dealing with. This is our x to the k plus 2. That says that converges on the same interval that the original series converged on, as long as the new power is larger than or equal to 0 for every single term in that series. So let me just write here by theorem 9.4, is that right? It's not 9.4, 11.4. By theorem 11.4, number 2, x squared over 1 minus x equaling this sum converges on the same interval that the original series converged on, as long as the new power, k plus 2, is larger than or equal to 0 for all terms. K starts at 0. Is k plus 2 larger than or equal to 0 for all terms? Yeah, I hope that's evident. So I'm going to just put this in parentheses because it's kind of we don't really need to say that once we've noticed that. So hopefully, you know, that gives you a concrete example to compare back to item number 2 and make a little bit more sense out of it. So the function x squared over 1 minus x is equal to the sum as long as we're in between 1 and negative 1 and 1. The same interval of convergence that the geometric series have. Do y'all have any questions?
So this last problem, you just use multiplication by power to the entire power, right?
Correct. And then we'll plot the function x squared over 1 minus x. So that's the sense of this function here, x squared over 1 minus x. And then we'll look at the series. But that happened pretty quick. Did everybody catch that? See how long it takes the computer to catch up. We're not going to get out very far, right? Because if we get out past negative 1, the series green is not going to match the function of black. Here's negative 1, and here's positive 1. Oops, here's positive 1 right here. I guess it's caught up. One more time. You know, it's not exact. In order for it to be exact, we have to add infinitely many terms. So even here, with 100 terms, you see that it's not exact, but that the difference between the function and the series is relatively small. 25.736. This is 25.737. Okay. Next example is similar. We're going to again use the geometric series f of x to find a power series representation for the function f of negative 11x. So here's where we're using composition now. We're replacing x and this function with negative 11x. That gives us a new function 1 over 1 plus 11x that we want to state the interval of convergence for. So let's look at it this way. We have f of x equals to 1 over 1 minus x, which is the sum from k equals 0 to infinity of x to the k, converges for the absolute value of x less than 1. Okay. But all we're doing is plugging in that negative 11x.
The f of x equals 1 over 1 minus x is equal to summation of x to the k.
Mhm.
That's right.
That's just the geometric series. We'll replace r with x. Yeah, so do you remember the geometric series was this?
Oh,
Yeah. And then that converges to a over 1 minus
That's
r.
if the absolute value of r is less than 1, right?
Right, yeah, that's the absolute value of r is less than 1. Converges to that. All right, so when we use function composition to create a new function equivalent to a series, then all we're doing is replacing the x in the original interval of convergence by the function we replaced x by. This new series here, I mean, we could write out some of the terms if we wanted to, but it really wants to know that series 1 over 1 plus 11x, what values of x does that converge for? Well, it converges for these values, which is 11 times the absolute value of x less than 1, which is the absolute value of x less than 1 over 11. The interval of convergence then is negative 111 to 111. Yeah, interval of convergence, yeah. And then, so that was just a quick example to show you that theorem number 3, in that last sentence, the composition converges absolutely to the composite function f of h of x for all values of x such that h of x is in the interval of convergence. So this is our h of x. The h of x is in this particular series interval of convergence. And of course, depending on what series you're dealing with, that interval of convergence might be different, right? If we were to look at that last function, or that last series rather, that converged on this interval from 1 to 3, then whatever we put in place of x, I'm gonna write this down, I think this was this series, x minus 2 to the k over the square root of k. So for convergence, x has to be in this interval. Right, including 1. So if I say I want a new series, I'm going to compose maybe x with negative 11x minus 2 to the k over root k. Then this has to be minus 11x minus 11x is in this interval. Does that make sense? So it's not that the initial interval is affected by the composition, but the composition does affect that because you still have to solve for x. So that's why we started off with the absolute value of 11, negative 11x is less than 1, because that was the original interval of convergence for the series given. Does that make sense? Here's some useful power series. After the next page, we could talk about, this is our geometric. You should know that one for sure. The second one below it, notice that's just, if I replace x with negative x, if x gets replaced by negative x, then I have 1 over 1 plus x, which gives me the alternating geometric series. So if x is replaced with negative x here, really the initial setup is that our composition converges. I replace x with negative x. This new function converges when the absolute value of negative x is less than 1, which of course is the same as the statement absolute value of x is less than 1. So there's your alternating geometric series obtained by replacing x with negative x to get this series. What about the sum of x to the 2k? What did we replace with? Do what? Yeah, we replaced x with x squared. And then we get this series. Oh. Yeah. It's just a replacement, obtaining a new series.
So if we memorize these, interesting, that'd be bad.
No, I think it's more efficient to memorize these than it is, because in the next section we'll show actually how these come about. And it's easier just to remember the Taylor series for a particular function than it is to find all of the derivatives, match them up with the coefficients, put those over the factorials times x minus a to the right. Remember all of that from 11.1. It's a lengthy process to construct that polynomial. It's easier just to remember these. What about the ln of x minus 1? How does that relate to 1 over 1 minus? Sorry, ln of 1 minus x. How does that relate to 1 over 1 minus x? Yeah, if I start with the ln of 1 minus the ln of 1 minus x and I take its derivative, what do I get? Negative 1 over 1 minus x, right? So that's where this negative is. This negative could be put in front of this. If I take the derivative of this function, I get this function. Another way to look at that is, if I take the antiderivative of this, I get this. So that's what the next thing tells us. We can differentiate and integrate power series, as well as multiplying, adding, and composing. Okay, we've got a power series, converges for this particular value. Remember, this is basically giving us our radius. And it defines some function f on that particular interval of convergence. F is differentiable, which implies continuity, which implies it's continuous. For the same radius of convergence, f prime may be found by differentiating the series of f term by term. So we just differentiate each term. Like the derivative of 1 is x, and then the derivative of x squared, the derivative of x cubed, the derivative of et cetera, et cetera. So we can take the derivative of each term in that series.
So, for problem 6 is just combining power series, right?
What was that?
Geometric series.
Yeah.
What, I was just curious, why didn't we test it on?
Because this theorem already tells us that this converges at the composition here with the same interval of convergence as the original. Because it said it was convergent on I, and that's an interval. So that I represented an interval. And so all of those, item 1, 2, and 3, always reference that original I as interval of convergence 2. Here we have to be more careful because this doesn't mention an interval of convergence, right? Notice it's got the absolute value of x minus the center less than r, which tells us that our radius of convergence is whatever that r is. It's the same thing here when we take the derivative. Term by term differentiation converges for the same radius of convergence. And notice we just take the derivative with respect to x, right, of this function up top. So that's just x to a power. The power comes out front to multiply that number, and then we take 1 away from the power. That's just our normal power rule for a derivative.
You're saying you're letting C of X, C of K.
Yeah, some constant. Could be different from each term, like 1 plus 2x squared plus 5x cubed plus. So those constants could be different, which is why they have that sub k there. Otherwise, it would be implied that they're all the same. Okay. And the same thing for the indefinite integral or the antiderivative. It can be found by taking the antiderivative of each term. So power rule again, we add 1 to the power on x and then divide by the result. Yeah, what we see is it has the same radius of convergence. We start off with some function represented by a series. We take the derivative or the integral, the antiderivative. The radius of convergence is still the same. However, it doesn't say anything about the interval like the last theorem did, the capital I, right? This only says that differentiating and integrating maintain the same radius of convergence, but the interval of convergence might change. So this theorem tells us nothing about the endpoints of a differentiated or integrated series. You must check the endpoints in the new series if you differentiate or integrate for convergence. The previous theorem said that if we add or subtract, multiply by certain powers, or compose by functions, you don't have to check the endpoints. If you integrate or differentiate, you do. Okay, so let's take a look at one example where we have the geometric series again. We're going to look at the antiderivative with respect to x. So, I mean, really, it's just one integral, right? There's just 1, 2, 3, 4 different ways to represent that function. It's all the same integral. Okay, keeping in mind that the original function, the geometric, converges for the absolute value of x less than 1. So what is the antiderivative of 1 over 1 minus x? Okay, it's a real thing. Does the antiderivative equal to the natural log of 1 minus x? Yeah, where's the negative? Yeah, because this is not log form. The derivative of negative x is negative 1, so we have a negative out front too. So negative out front of the logarithm. Okay. Let's see what that is term by term. What's the antiderivative of 1? Close. It's x plus 1x squared over 2, yeah. Plus 1/3 x cubed. I don't know, one more perhaps. Okay, so that's the antiderivative term by term. Here we have the antiderivative of x to the k with respect to x. So that series would be what? All right, yeah. Where does k start? Zero. So we got x to the first over 1 gives us x. X to the 1 plus 1 over 1 plus 1 gives us x squared over 2. Yeah.
Is there not a constant like that?
No, we didn't multiply by a constant or anything like that. Is that what you're referring to?
Yeah.
So there's the antiderivative. Remember, the original series converged for the absolute value of x less than 1, meaning that the interval of convergence for the given geometric was -1 to 1. So then we've got to ask, does the negative ln of 1 minus x, which is this series, does that still converge for those values? Okay. One way we can sort of fix the x plus 1 or the k plus 1s, remember, if we subtract 1 from our argument, or the summation part, the sum end, well, what do we do to the index? If we subtract 1 here, what do we have to do here? Yeah, if we subtract 1 from this, we have to add 1 to this. So we could rewrite this just to clean that up as x to the k over k when k starts at 1. Okay. It's the same thing, same representation, or different representation of the same thing, I should say. You got to test the endpoints of the old interval of convergence into the new series because we took an antiderivative. Same is true if you take a derivative. Okay, so when x equals to -1, our series is -1 to the k over k. What do we know about that series? Alternating harmonic, the alternating harmonic series converges. So we've got to include -1 in the new function, new series interval of convergence.
So why did you choose Brown though? Why did you-
Just to clean up this, instead of having x to the k plus 1 over k plus 1, starting at 0, it's x to the k over k. It's just that summand is a little bit more clean now. How about when x is +1? Well, then you get the sum from 1 to infinity of 1 over k. And what do we know about 1 over k? The sum of 1 over k to infinity. The terms go to 0, but the series diverges. It's the harmonic series. The harmonic series diverges. So we still exclude 1 for the interval of convergence. Yeah. So let me write this here. Therefore, the series for the negative ln of 1 minus x, that's equal to the sum k equal 1 to infinity of x to the k over k, converges, or is, we'll just say valid for, same thing. So this function equals that series for this interval. Radius of convergence is still 1. Because our center is at 0, 0 to 1, 0 to -1. So this material is probably new for most of you. You see that it just never stops. There's always something new, right? You really gotta, I hope that you're staying up with the homework. I think otherwise, most of you are attending class regularly, so I assume you're staying up. Otherwise, you're kind of in a jam, I think. Yeah, see that.
How do you know, when it comes to tests, how do you know what which one is?
Most of them, it's hard to determine. Therefore, on the exam, most of the questions I will say use this test to show. With these types of problems, though, where you're given a power series and it says, you know it's a power series if you have a variable x in there, right? So those are always either the root ratio or it's geometric. As far as this like generic series, like this one, I would know if I want to test the interval of convergence for that, I'm going to use the ratio test on that. Test the endpoints. But if that's just like k factorial over k, then I have to use like a ratio test. So on those, I would say use test XYZ to determine convergence. Some of the other things should be obvious, like when factorials are involved, you use the ratio test regardless. The geometric should be obvious. So with some of the obvious ones, maybe I might not say, I might just say test for convergence, and it's up to you to say, oh, hey, that's geometric, or that's factorials involved, I need to use the ratio test. Other ones will be explicit. I think that's it for 9.2.
11.
Yeah, 11.2, yeah. Whereas 9.2 lessons. Did everybody get the sign-in sheet? All 12 of you. All right, now this is where we kind of put 11.2 and 11.1 together. Really, so the issue at hand in 11.3 is if we're given some function, what is that function's Taylor series? Remember, a Taylor polynomial is a finite polynomial. A Taylor series is an infinite series. So notice here now we're summing out to infinity as opposed to 11.1 where we summed out to just n. Same coefficients, same structure, we're just taking it out to infinity. Find the Maclaurin series for e to the x. What is the Maclaurin series? Yeah, Taylor series centered at 0. Yeah, I just don't know how many people actually read those. So. You should have just went with it. Like, yeah, I totally remembered that from 9.1. 11.1. So it's the same process. Hopefully you remember what we did in 11.1. We looked at the function, evaluated at the center, its derivative at the center, second derivative at the center, right? And then in that instance, we would just stop at like 4 or 6 or whatever the nth degree Taylor polynomial we wanted. Here we actually have to come up with a summation formula for the infinite polynomial. So we did a lot of this in 11.1. So we find the function, the first derivative, second derivative, etc. All evaluated at the center, which is 0 because it's a Maclaurin series. So just do that because all derivatives are e to the x. F prime of 0 equals to 1. All subsequent derivatives evaluated at the center are also 1. Is everybody okay if I do that? Clear? So then we've got to remember the structure of the series. We start off with the function value. So we start off with f of 0, which is 1, plus the first derivative times x minus the center to the power of 1 over 1 factorial. And we continue that pattern, plus the second derivative's coefficient times x minus 0 squared over 2 factorial, plus coefficient from the derivative times x minus the center third, because that's coming from the third derivative over 3 factorial, etc., etc. Let's just simplify that or clean that up a bit before we put an actual summation to it. We got 1 plus x squared over 2 factorial plus x cubed over 3 factorial. Now we want to write that as a sum. So what is that sum? what's the pattern here to the? Yeah, x to the k over k factorial. K starts at 0 to get that 1 as the first term.
But what is that?
It's all the numbers you receive.
Like what?
So remember, this is saying that our function is actually equal to this polynomial. Our function was f of x equals e to the x. So really what we're looking at is this really e to the x? I guess at this point what we're saying is we constructed that Taylor polynomial. Is that e to the x? Well, we have a series, a power series, x to the k over k factorial. Now we can test for the interval of convergence. So now we go back to our previous section. The interval of convergence. How are we going to test x to the k over k factorial? With what test? The ratio test. So we have our ratio is limit k approaches infinity. You'll recall that we did this one already. So there's a ratio applied to the series representation for what we think is e to the x. So what do we have left over? We have x k plus 1 factorial gives us k plus 1. Which is 0, right? The limit is 0. Okay, so that's our ratio rather. For convergence, we need the ratio to be less than 1 for convergence. Less than 1 for convergence. When does our series converge? For all values of x, because our ratio is always 0. No matter what value of x we plug in, the ratio is always 0, which is always less than 1, which means that function always converges.
So any value for x over.
Yeah, so therefore, any value of x will result in a convergent series. So we can write this down next time. I know we're out of time. We don't have to worry about what x is. That polynomial is equivalent to e to the x, is equivalent to that power series for all values of x.
So we could just do like negative infinity
Yeah. We would say the interval of convergence is negative infinity to infinity, and the radius is infinite. Pick up there on Tuesday.